Hello and welcome to this session. In this session, I want to talk about the solutions to transcendental and algebraic equations using what we call the Newton-Raphson method. Remember, the Newton-Raphson method, when we talk about the Newton-Raphson, method for solving the equations, this one is an iterative procedure that solves the equation of the form f of x is equals to 0. For example, you may be looking for the root of the equation x cubed plus x minus 1 is equals to 0. And maybe you have determined the initial approximation using some method such as the intermediate value property. You may determine that the root exists between 0 and 1. Once you know that the root exists between that, you make some initial approximation, say x naught is equals to 0.5. Then once you know the initial approximation, you want to obtain a better approximation. So you use what we call the Newton-Raphson iterative method that says that if xn is an approximation to the root of the equation f of x is 0, then a better approximation is denoted by xn plus 1, as is defined by this formula, f of xn minus f prime of xn. That if xn here is a root, an approximation to the root of the equation is f of x is equals to 0. This is the equation we want to solve. So if xn is an approximation to the root, then a better approximation is given by this. So we think of an equation such as this. We determine using a method such as the intermediate value property that there exists a root between 0 and 1. Then we make an approximation of the root by picking any value in between 0 and 1. We can pick a value such as 0.5. Then we implement now the iterations using this method. So we start with n is 0, that will give us x naught, which we have picked, and then compute x1. Once we increase n from 0 to 1, then we can compute x2 and so on. So when we are solving this equation, what do we need to do? We need to know the function f of x. This one should be known. Then compute the derivative. We can call it df of x, which is equals to f prime of x. And then the next thing is the initial approximation. The initial approximation, which we can call x naught. And then the next thing is to do the iteration. Do the iterations. So we're using the formula xn plus 1 is equals to xn minus f of xn divided by what we can call d f of xn, where d f of xn is the value of the derivative of the function f of x, the value of the first derivative of the function f of x when x is equals to xn. Now, when using Matlab, how can we write this? How can we do this? So Matlab, we want to solve the equation. Our equation is x cubed plus x minus 1 is equals to 0. And we want the root which is near x naught, which is 0.5. This is our initial approximation. This is the equation that we want to solve. So How can we implement the method in Matlab? The first thing is to create a symbol in Matlab. We can call this symbol x. So we use the command syms, then x. I'll use small x here, so that that creates a symbol in Matlab session. Then we now create the symbolic function. I'll call it f of x. And remember, I'm using the small x. So the function is x cubed. And that's not how we write x cubed. So I'll use the hat 3 plus x minus 1. Then to constrain the output, you put the semicolon there. Then compute the first derivative. So I'll call it df. So using the diff function in Matlab, you want the derivative of f with respect to x, and this is the first derivative. Then I'll put the semicolon there to constrain the output. Once the function and its derivative are determined, you need the initial approximation. The initial approximation x0, which is 0.5. I'll call this capital X1, which is 0.5. So here, I'll use capital. So 0.5 and constrain the output. So I could have called it X0, but Matlab normally does not accept the index 0. The indices in Matlab starts from 1. So I'll not write 0 here, I'll write x1, not x0. I could have written x0, but now Matlab will not accept 0 as the index. So I'll use x1. Then the other one would be x2 and so on. So once we have these values, then I can do the iteration using the loops. Now, which loop do I use? I may want to use the for loop. So I'll write for n is equals to, now remember, n will start from 1. But now, when using the for loop, I'll need to know the number of iterations that I need. I need to know this in advance. So I can maybe use 6 iterations. So I'll write for n is equals to 1 to 6. What do I need to do here? I'll compute x. I'll write x n plus 1. I'm using capital X is equals to xn minus f of xn divided by d f of xn, and constrain the output here by putting a semicolon. Then we have the add statement, but before the add, maybe I want to print the output of each iteration. So I'll use the fprintf function and write maybe x underscore. I'll put the placeholder, which is the percentage sign. Here I'll just want to place the value of n. So n is an integer, so that I want to have x1, x2. I want to write x1, x2, x3, and so on. The iterations, the iteration values. So I'll put the value is an integer, so I'll use d. So then this is equals to, and now I'll put the value that is computed. So I'll put the percent sign again, 0.5. I want to use 5 decimals. I want to place the results as a floating point decimal, correct to 5 decimal places. Then now this, I'll put the escape character and then comma. Then I have x, comma, x n plus 1. And close the brackets here. Then we have the add. So when I run this one, what will happen? The first statement here will create a symbol called x, small x here in Matlab. Then the next line will create a symbolic function. And then the next one will differentiate the symbolic function with respect to x. Then the next line will create the initial approximation, which I'm calling x1. Here is capital. I want to differentiate the symbol here, which is x, with the values of the iteration, so I call them capitals. So when I go to Matlab and learn this, I can open a Matlab session and learn this one. A Matlab session and learn this one. So I want to start with creating the symbol x. The next thing is the function f of x, which is equals to x raised to power 3 plus x minus 1. I put a semicolon. The next one is df, which is equals to, we have df f comma x comma 1. This is the first derivative with respect to x. Then the initial approximation, x1 is equals to, we have using 0.5 as the initial approximation. Then I'll write the loop. For n is equals to 1 to 6. I have said that I want to use 6 iterations. Then I have, I have xn plus 1 is equals to xn, then minus f of xn, and then we divide this by df of xn. I constrain the output here. Then I print the output using the fprintf function. So I put x underscore, then I put the percent d is equals to, we have the percent f, I'll put 0.5 because I want 5 decimal places. Then n comma x n plus 1. Now what I've omitted here is the escape character. That may not affect the solution, the results, even if I omit it. But suppose I omit it first, then we see what happens when I run this one. The results will still be generated, but there will be one problem. There will be one problem, that the results are all in one line. x1 is equals to x2 is equals to that x3, but that is not the way I would want the result. So I put the escape character so that a new line is created after every output, so that now I have some better results, x1, x2, x3, all the way up to x6. Now here you can see that x1, x2, x3 are different, but all the others are the same as x3. So probably I did not need to do so many iterations. But how would I have known that I needed only 3 iterations? That may not be possible to know in advance. But a better way of doing this is to use the while loop. So let me use the while loop. I want to first clear all the variables, so all the variables in the workspace. Then I use the while loop. Now I need to specify some condition here And the best condition that I may want to write here is the error. What is the maximum error that I may want to accept? Let me call it some tolerance value, which is 0.00001 maybe. And then I don't have n here, but I still have n in my formula, so I'll put n is equals to 1 up there. Then, because I'll still need to increase the value of n, I'll put the incremental statement here, n is equals to n plus 1, so that the value of n is increased after every iteration. I'll now put the condition here for the absolute value of the function f evaluated at xn, for the absolute value of the function is greater than my error value, which is the tolerance here, then we do this, so that the loop will stop when the absolute value of the function is equals to the tolerance or less than the tolerance. But as when it is greater than the tolerance, the loop will continue to execute. You see, now this one will determine that I don't need to know the number of iterations that I need in advance. I will just learn, and the loop itself will determine. I just need to know the maximum error that I may want to allow. So when I run this, I see that I want to get 3 iterations. And unlike the other one where I needed to do 6 iterations. Here I'm only getting 3. Because the loop itself will determine that the error has, the conditions here has been met, and I don't need to do any other iteration. So a while loop can be a better loop when you don't know the number of iterations that you need to do. But all in all, each of these will produce the same results. Will give us the same results eventually. But you note the structure is the same. First is to define the symbol, create the symbol in Matlab session, then the symbolic function, and then the derivative of the symbolic function, the initial approximation, and then the loop. Then you print the output. Now, if you don't want to print the output of every iteration, and probably you want to just the last value, I can put this value after the add statement, so that I do the iterations here, and so once I have done all the iterations, I'll print now the value. I'll print the output. Notice that I've written now xn here. I'll print only the last value, which is x6, which is 0.68233. If I do the same here, I remove this one here. I print this one after the last statement, and I want to clear the elements here so that I don't print the value of the other method, the other loop. I run this one. This one prints x4. This one prints x4 is that the 4th iteration. And we had said that we are going up to the 3rd iteration. But n has increased to 4 here. So when I use n here, maybe I should have used n minus 1. Yeah. Because this one is increasing. After computing the value here, the value of n is increased by 1. So maybe I should have used n minus 1 here and n minus 1 here. Then I'll print the values, the correct value, x3. But that one is, no, this one should still be n, because we have n plus 1 here, not n. Even if this one is increased, but this one is n plus 1, so it's the n plus 1. So that one should be xn. So that one prints the correct value. So the first one prints x6, the second loop prints x3. That is the same value, because this one did only 3 iterations, while this other one did 6 iterations to get. The value was still obtained after the 3rd iteration, but the loop, we had said that we want to do 6 iterations, so it still continues to do the other iterations even without getting a better approximation of the root. So basically, this is the structure. You have the symbol, create the symbol, create the symbolic function, differentiate the function with respect to x, enter the initial approximation. If you are using the while loop, you need the tolerance value and the value of n, then do the iteration. The formula is just the same way you would write it in our book, and then print the output. So basically, that's how we implement the Newton-Raphson method in Matlab. That's how we implement the Newton-Raphson method in Matlab. It's a procedure to do, but it is important that you enter the values correctly in each step. Don't make errors here. And notice that I've used x here, small x here, and capital X here. Maybe to avoid confusion, maybe we can use, we can call this one y, and maybe you can call these values y to avoid the confusion with the x's here. Because the x is a symbol and these are values, we may not want to call them, to use the same thing, a symbol and a value. Because if you start now using small x here, there will be some confusion. Which one? Where do you use the symbol and where are you getting the values? So probably one way, instead of writing the capital X and small x, is to use another symbol like y. Then you learn and you get the same thing. You get the same thing, only that now your results are generated in Matlab as y's. Y1, y2, y3, y4, and so on. But if you want to use x, you can use small x here when defining the function, and capital X when you are computing the roots. So thank you for listening to this. I think in the next video I'll talk about the regular falsi method.